Yay!
Yay! We've done a lot of examples with point charges. So now let's try something different. Let's go to more, if you like, real-world objects that are not just ping-pong balls of charge or elementary particles, but actual physical objects like rings and sheets and so on that we can charge. So this first one is usually the one, the simplest to start with. And so let's imagine you just have a ring. So in the XY plane, suppose I have a ring of charge. Suppose I charge this thing up, it's metal or whatever. Don't worry about its thickness. So a thin ring, and we charge it up to plus Q. And what I'm interested in is along the axis through the center of the ring. So here, like along the Z-axis, I want to know what the electric field is at that point on the on the Z-axis. All right. So the usual prescription is, what we've been doing is we said that the electric field is, I'm going to leave a little bit of space, kq over r cubed r vector. Where there are components involved, we can write it like this. And then if there's a whole bunch of charges, what we do is we just sum them all up, right? Each charge, little I just sum all those little things up. This is what we did before. So I have a different kq over r cubed r vector for each charge. I sum all those electric fields together, and then I get the final electric field. So what I'm going to do this time is the same thing. The problem is that we don't have individual charges. I got a whole ring of charge. And if you think about it, what you've got is you've got little positive charges, if you want to think about it that way, or lack of electrons, right? That's how you would positively charge the thing, is you take electrons away. But anyway, around the ring, you're going to have, I mean, trillions or Avogadro's number of these things. And so, it's not really practical to actually add them all up, if you even knew where they were to begin with. So instead, what we do is we assume that they're uniformly distributed around the ring. And since there are so many, we replace that sum with an integral sign. So what we do is we chop this thing up into lots of little tiny dq's, in like the calculus sense of the word. So that would be a little bit of charge dq, and then I add up. And we know that in calculus, the integral symbol is basically the summing symbol, right? So I'm going to add up all these little charges, k dq over r cubed r vector. Well, that's what I'm going to do. So I'm just going to integrate. I'm going to add up all these little teeny tiny charges. But I have to think of some way to do it around the ring. And so this is where your mastery of calculus, I don't know what it, Calc 2 or something, I don't know what it is. This is where your mastery of calculus is going to come in handy to figure out how we're going to integrate around the ring to get the answer. All right. So let's think about this. This is a circle, right? And so I want to integrate around the ring. Here is the line, the vector from the charge to the point I'm interested in. And let's say this is that's going to be our distance r, right? From each little thing, but going all the way around, that vector is going to change. So from that dq, I'm going to have a little electric field vector going like that. Okay, so I'm going to want to integrate all the way around. What you'd like to do from calculus, it's just around in a circle, right? So the most natural thing is you're going to want to integrate from 0 to 2 pi because you've integrated around a circle before. The problem is that would be integrating a d theta, right? We're integrating an angle from 0 to 2 pi. That's the thing that changes from 0 to 2 pi. But what's in there is a dq, a charge. So here's the trick. This is a trick we're going to use over and over again. We need to change variables. We need to find some relationship between a little bit of charge and the angle. And so here we go. Here's our little trick. I'm just going to write something down, and what I'm going to write down is just I'm not deriving it from anything, it's just a mathematical sentence. It's just a ratio. So here's what I'm saying. A little bit of charge compared to the entire charge all the way around the ring is the same as a little bit of angle compared to the total angle all the way around. And what's the total angle all the way around? 2 pi. Right? That's just a ratio. So you can say it in language. A little bit of charge compared to the whole charge is like a little bit of angle compared to the whole angle. Really, all I'm saying is that the charge is uniformly distributed. This is what it means. So now I can do this. Look, now dq is just q d theta over 2 pi. Pretty cool. And so now I can just zoop. I can just plug that right in. And now I'm going to have a d theta in there. So I got this. So this means my electric field, actually, I have something in mind. I'll put it down here. So now my electric field is going to be the integral, 0 to 2 pi. I'm going to have a k, and instead of dq, I have a q d theta over 2 pi. I still got an r cubed down here, and I still got this r vector. And what that means, that r vector is inside the integral. It means I still got to add up all of those little r vectors. Because around the circle, the direction of r vector is going to change as I go around. All right. Well, certainly k, q, and 2 pi, that can come outside the integral. That's fine. Let's see. Oh, what about r? What about the distance? As we go around the circle, that distance r, from the point, from the dq, from each little charge, the distance r up to the point on the z-axis, that doesn't change, right? That's the same all the way around the circle. The distance, r cubed, that doesn't change. So that can come outside the integral. So my integral becomes this, kq over 2 pi. By the way, let's do this. Oh, I'll fix it in a minute. That's okay. I'll just call it r cubed. I'm going to call it something different in just a minute. And so what I've got left is 0 to 2 pi. I got a dq. I'm sorry, d theta, and got my r vector. Okay. What is r vector? Okay, let's look at this way to figure that out. Now, some ways, if you look in different textbooks that solve this problem, they solve it using sines and cosines and so on, which is fine. There's a number of ways that you can do it. I would like to show this way because this is a powerful physical principle, something that physicists do all the time, is invoking symmetry. For example, okay, look where I have the dq drawn right there. What is the vector r at this point? The vector r, remember what that is. The definition is it's from the charge to the point I'm interested in. So how do I get from that little bit of dq up to the point on the z-axis? What do? Well, I have to go minus the radius in the x direction. I don't do anything in the y. And then I have to go up z to get to the point, right? So that's my vector r from that point. Now, if you think about it, we're summing these things all the way around the circle, right? So at some point, we're going to be back here on the other side. And when you're back here, let's see if I can draw this. What is the r vector when you're back here? When you're back here, how do I get up to that point? I go plus r in the x direction. I don't do anything in the y, and I go up z in the z. Right? Those two things, amongst all the others, those two are going to be added together. And when I add those vectors together, what happens? The x coordinate, or the x component, goes away. All I'm left with is z. All right, so you can start to see what's going to happen. The only thing I'm going to be left with is a z component. That kind of makes sense if you think about all those little DEs, like the DE is going in some direction, and as I go around the circle, all those little electric fields are going to form kind of a cone, right? And when I add all those electric fields together, the only component that's going to live is the z component. So it kind of makes sense that the final electric field is only going to be pointing in the z. But here's how we're showing it. Okay, and then just to make the point, if I'm over here, look at this little bit of charge on the y-axis. what's the r vector from that point up to the point I'm interested in? I can write that down. What do? I do nothing in the x. I go minus r in the y and z. But then that's going to be balanced when I get around to this side, because that's going to be 0 plus r and z. So once again, the y coordinates are going to vanish, and still I've got that z, right? So you can kind of convince yourself that no matter where you are on the circle, if you're right there, right, it's a combination of x and y. But that's going to be exactly balanced by its partner on the other side. So as you go around the circle, always the x and the y components are going to vanish. They're going to add together to be 0, but you're always going to be left with that z. So the final, that r vector, when I integrate that r vector all the way around, the only thing I'm left with, the sum of all those r vectors is just going to be z. That's it. It's got a magnitude of z in the z direction. So what's going to happen is that my electric field, I'm just going to have that constant factor of z, which doesn't change, right? Z, that distance up the z-axis, that doesn't depend on where I am around the circle. So that comes outside the integral too. So I just have k, q, z over, okay, let me write this a different way. 2 pi r cubed. That distance r, what is that distance r? The distance, well, it's just a right triangle, right? That's just going to be this distance squared plus that distance squared. So that's just going to be r squared plus z squared, and it's cube. That's the square root of it, right? And then we cube it, so it's going to be to the 3/2. And then I just have the integral from 0 to 2 pi d theta. Oh, well, that's easy. What's the integral of d theta? Theta. From 0 to 2 pi? 2 pi. I mean, in words, all you're doing is you're adding up all the angles from 0 to 2 pi, and what do you get? You get 2 pi. That's not tough. So that 2 pi just cancels that whole integral, right? So here we go. We're done. So the electric field, oh, I got a vector on the left-hand side. I better have this indicating direction on the right-hand side, right? It's in the z-hat direction. So what I've got is kqz over r squared plus z squared to the 3/2 in the z-hat direction. That's it. That is, apparently, the electric field from a ring of charge along the z-axis. Okay, is it right? I don't know. I mean, you can look it up in the back of a book, I guess, because people have, of course, done this before. It's a standard exercise. But let's look and see, is it likely to be true? Let's see if it's probably true. Let's look at it in the limits. Let's see if this makes sense as a solution. If I go really far away, what I mean is, far away from the ring, z is way bigger than r, right? What happens if you get really far away from a ring? What does it look like? If I have a little ring of charge and I go a half a mile away, it's going to look like a point, right? You can't resolve that it's really a ring anymore. So if I go really far away from this thing, the electric field should look like that of a point charge. Let's see. If z is a whole bunch bigger than r, then the z squared term dominates the r squared term. And so it's just z squared to the 3/2, and that's z cubed. So that would be E is about kqz over z cubed. Oh, but that's it, isn't it? That is kq over z squared. Neat. So this is saying, as z is a whole bunch bigger than r, if the ring is teeny tiny, then the electric field really does look like the electric field of a point charge. That's really neat. So this does stand a chance at being right because it's got the right limits. What happens down in the center? If z is 0, what happens if z is 0? If z is 0, what's the electric field? Well, I mean, just look at it. If you're down here at the center, I've got an electric field from, if you're right here, the electric field from this thing is going that way, right? Electric field from this bit is going that way. Electric field from that bit is going that way, and so on. So at the very center, all of those arrows are going to cancel. So it makes sense that at the center, the electric field should be 0. So look back up at our formula. If z is 0 in the formula, oh, well, sure enough, if z is 0, the whole thing is 0. So electric field is 0. So that checks out. So that's cool. So this has the right conditions that we know must be true. So this has got a good chance at being true. Look, there's something really cool about this, and I want to spend just a little bit of time because bandwidth is cheap, right? I don't care. Also, disk space is cheap. Look at this. Look at this. Look how cool this is. What if I were to graph? Look at this thing in graph E against like R. What we're saying is, or Z. E against Z. Okay. When Z is 0, E is 0. Okay, no problem. And then, so as I go to the right on the graph, I'm going up the Z axis. So Z is 0 right there. But then we're saying that when Z is really, really far away, the electric field is dying off as 1 over R squared. So how does a function start at 0 and then die off towards 0 at large Z? What this is telling you is that somewhere in here, the function must have some sort of a maximum, right? It's got to turn over. And functions that have a local maximum or minimum are really cool. You can look it up in a math book. It's called Cool. So now what I'm kind of wanting to do is I want to see where is the electric field a maximum. So in other words, as I'm going up the Z-axis, the electric field is going to get bigger and bigger and bigger, and then it gets to a maximum, and then it starts dying back off again. This isn't obvious to me. When I look at the ring, it's not obvious that this thing has a max, but apparently it does. This is a neat function. So let's find it. Let's find where the electric field is a maximum. How are we going to do it? Okay, I'm out of room, so let's go over here. The electric field is kq, just the magnitude of it is kqz over r squared plus z squared to the 3/2. Oops. Move that down here so we can actually see it. How do we find out where that function has a maximum? What we do is we find the derivative of the function. And what do you do to see if it's where it's a maximum? You set it equal to 0, right? So let's do that. Because if this is some function, the derivative is just that tangent of the slope. There's slope of the tangent to the curve, right? And right up here at the maximum, the tangent is going to have slope 0. It's going to be horizontal. So we want to find out where that function has a maximum. So let's take the derivative and set it equal to 0. What is dE dz? Well, it's not terribly simple. We can do it. Let me rewrite this. This is kqz. That's the first part. I guess you could use the quotient rule, but I'm going to tell you a little secret. Nobody ever uses the quotient rule, like ever. So there's no need. You don't need to do it. So this is going to be r squared plus z squared to the minus 3/2. Now it's a product. This is why no one uses the quotient rule, because you can't remember it, and you can make everything into products anyway. So, okay, so here's a product. It'll be eventually a product in a chain rule. So I'm going to take the derivative of this thing. So it's a product. So, okay, so I'm going to take the derivative of the first thing times just the second thing. And so this is going to be, what is it going to be? KQ times the second thing. Okay, I'll just write it back down here. R squared plus z squared to the 3/2. And then I'm going to have a first thing, KQZ, times the derivative of the second thing. Okay, well, it's a thing to the minus 3/2 power, so I got to bring the minus 3/2, so that's going to make that minus KQZ times 3 halves times the thing, r squared plus z squared, and I decrease the power by 1, so it's going to be minus 5 halves, times the derivative of the thing. There's our chain rule. So this is going to be times 2z from inside that z squared. Okay, and all this is going to equal 0. Cool. Okay, so this 2 and that 2 is going to cancel. So let me just do a quick eraser thing here. So let's get rid of that. And I'm going to bring this over to the other side. So those are equal, right? I'm just saving a little time from rewriting everything. And now the KQs go away. Very cool. So I've got 1 over to the 3 halves is, what do I have on top here? 3, what's left? Z squared. And then I've got this thing, r squared plus z squared to the 5 halves. There we go. All right, so let's bring the thing to the 5 halves over to the left-hand side, and then that just leaves me with the thing to the 1 power, right, to the 2 halves. So that's going to be r squared plus z squared equal to 3z squared. Okay, so r squared is equal to 2z squared. Oh, then I got it. So this thing is a maximum where z is r over the square root of 2. There we go. That's where it's a maximum. So what is it? That's like 1 over square root of 2. What is that? Like 70% or something. So that's something like 0.7 r. That's where this thing is a max. So if we go back to here, wherever r is, you know, some point, maybe it's right there or something, that's where the electric field is a maximum, at r over the square root of 2. Very cool. And if we want, we can put that back in. What is the electric field at that point? It's just going to be kq times r over the square root of 2 over r squared plus a z squared. What is that going to be? R squared over 2 to the 3 halves. Cool. When you simplify, it's just a boring algebra. At the end, I get, what did I get? So E max is, what did I get at the end? 2kq over 3 root 3. Check my algebra. I think I did it right. R squared, something like that. Okay. So anyway, just to show that at the end, here's what you would actually get. What is the maximum electric field? If you know the K and the Q and the R, this is, well, you know the K. If you know the Q and the R, this is what you would get for the maximum electric field. So on the graph, there we go. That would be the max. The one thing we didn't do yet is, what does the function look like when you're close? How does the function behave when you're close? Let's see, what do I want to, where, oh, kind of open over here. If z is much less than r, what does the function look like if z is much less than r? That's the one thing we didn't do. Well, there's the electric field up there. If z is much less than r, then the r term dominates. So this is just going to be kqz, about kqz over, that's going to be like r squared to the 3 halves, so that's r cubed. So let me write it like this. This is a little more suggestive, like that. This is linear, right? Because that's just like y equals mx plus b. Here b is 0. So it's just kq over r cubed. That's just the slope of the line. It just goes as z. So if we're filling in the graph over here, it's a linear slope for small z, and then you hit some maximum, and then it starts turning back over. If you look at a graphing program or graphing calculator, you can see what it actually looks like. But we know the behavior of this thing. So starting at the origin, the electric field is 0. And then as you go up, the electric field starts growing linearly with your distance. And then it hits a maximum, and then it starts turning around and decaying. It goes down as 1 over r squared. Very cool. So this example, sometimes this is they call it, I mean, this is usually the simplest example in most books, but there's a lot of cool stuff in here with this example. And now that we've done it, now that we've integrated a ring and we know the electric field due to a ring, now we can do more complicated objects that we can build out of rings. And so that's going to be very cool too.